When we're calculating normal strain and shear strain, there is this kind of shortcut we can use to calculate these things. Sometimes the trigonometry of our shapes can get really complicated when we're having these things move around. But in most of our engineering applications, the deformations are going to be really, really small, right? Your normal strain is often way, way less than 1, right? The double less than signs means way, way less. Your shear or your normal strain is going to be way, way less than 1. They're going to be super small. So small that we can often simplify these calculations with something we call small strain analysis, or you'll also see it called small angle theory, which essentially says, hey, these deformations are so small, we can actually shortcut them using S equals theta r. Right, so distance, right, the change in distance here, S, change in position here, S, can be the angle theta in radians times the original radius out, the original length out. Right, instead of getting into really complicated trigonometry, which sometimes can be the case. You get mixed up in law of cosines and things like that, whereas we can say this is a close enough approximation instead of going through the actual trigonometry of what's happening. So let's take a look at an example of what that would look like. So in this example, we're going to take a look at how you'd have to solve this problem the long trigonometry way versus using the small strain analysis method. So in our problem here, it says when force P is applied to the rigid lever arm ABC, the arm rotates counterclockwise about pin A through an angle of 0.05 degrees. Determine the average normal strain in BD. So BD is this wire that's connected to this lever, and somebody's pushing down on the lever, and we need to find what the strain in that wire is. So if I were to draw this out, what does it look like when the force is applied, right? How does this triangle change? How does this triangle deform if we were to think of this area here as a triangle, this ABD, this triangle here, because this is what's kind of changing. This is what's moving, right? If I draw my initial way it looks, I have this 300 millimeters, 400 millimeters. This is A, B, and D, which of course this is a right angle. It's a 3, 4, 5 triangle. So I know this distance between A and D would be 500 millimeters, right? So that's the initial condition. And then once it goes through that strain, that lever is pushed down. So I'm going to draw it as like a dramatic effect, but it wouldn't actually be undergoing this much deformation, but our triangle would look something like this. D and A both remain in the same location because it's rotating about pin A. D is attached to the wall there. B is what's moving. Right, so now our wire is down here at B prime. B is in a totally new location. And we'll notice that 2 of our lengths are still the same here, right? The lever moved down, but the length of the lever between A and B is still the same. That's still 400. The length between D and A is still the same. It's still that 500. But now this length DB is not 300. It has some new length. Length B prime D is different. And we would have to find what that is. Now it tells us that it rotates through an angle of 0.05 degrees. So that's telling us that it's going from this original angle here, the angle of the 3, 4, 5 triangle, and adding half a degree to that. So this angle here is that 0.05 degrees. So if I punch this into my calculator, let me calculate really quick what this original angle here is. So let's call this angle, let's call this theta here. So theta is the original angle that it was sitting at. And that we can get from arctan, inverse tangent of 300 over 400, or we could use the 500 and 400 with cosine or sine, whatever method you want to work out with that. But I'm just going to leave it with this one. So that initial angle is 36.87 degrees. 36.87 degrees. That's this here. And then it adds that additional 0.5 so that the new angle of this triangle, let's put it in red maybe, so that theta plus that 0.05, we'll call it phi, is theta plus that 0.05. So that new angle that we have there is 36.92 degrees. And then you're like, okay, great. Now I can figure out what that length is. And how do we do that, right? Because it's not a right triangle anymore. It's now, well, it's not a right triangle anymore. So it makes things a little bit harder for us. We can't just use Pythagorean theorem or something nice like that. We can't just use sine, tangent, whatever. We're going to have to use law of cosines. So law of cosines, if you'll recall, and I don't, so I had to Google it, right? Law of cosines. To get this length of b prime d. I'm actually not going to use this color. Yeah, okay, give me that in white. The length of b prime d, to calculate that, it's the square root of your length a, well, I'm going to use the general form. So a squared plus b squared minus 2ab cosine, well, in this case, phi. Where here our a is going to be that length of 500, right? The length of AD. And b is going to be the length of 400, the length of AB prime. So it's these two sides that make up the angle between phi. That's why we want to use law of cosines, because it is a side angle side triangle. Well, you probably didn't think when you were learning trigonometry in, I don't know, some of you guys take it really early, 7th grade, that these triangles would come back to haunt you so much. But here it is, trigonometry. It just won't leave us alone. So b prime d, the length of that is going to be square root of 500 squared plus 400 squared. I'm just going to leave everything in millimeters, so I'll get an answer in millimeters. Minus 2 times 500 times 400 times cosine of phi, 36.92. Punch that puppy into my calculator. I get my length of b prime d is 300.3491 millimeters. Whew. All right, and what did we do all that work for? Find the average normal strain? Right, so we still have to punch in our normal strain equation. Right, our normal strain equation for, what is it, BD? BD is the new length minus the initial length over the initial length. So that new length is 300.3491 minus the original length was 300 all over 300. So that my strain is 0.00116 millimeters per millimeters. And that's my answer. Right, so that was kind of a long way to get there, a lot of trigonometry. So let's take a look at this small angle theory, right? This small strain analysis. How would we do it if we didn't pay precise attention to this trigonometry and we just used the shortcut? S equals theta times R. All right, so S equals theta times R. S is going to represent our delta. So that changed. So if we were to take our triangle again, instead of saying that our triangle is being fully shifted over like this, that has this new angle, we're just going to say, all right, well, what if instead in my triangle here, I have, it goes through this angle downward, right? So here's D, A, B, but I'm essentially just assuming, all right, what if B just kind of goes down, straight down, right? Straight down, and then I have this little, you know, here's the 0.05 angle that it's going through, but B prime is basically directly beneath, instead of saying that it's fully kind of tilted over at this angle. So here I have my S equals theta R, where our theta is that angle, that 0.05 that they gave us. But we'll need to convert it to radians. And this S, so S is the delta, which is this distance here. This distance here is our delta. Our S is the theta times R, where R is the radius of this arm here. So this distance is R. This angle here is our angle theta, and then this distance here is S. So S equals R theta, S equals R theta. Or D equals R theta, where our theta is 0.05. That's in degrees. We need to convert it to radians. So to convert to radians, you just multiply by pi over 180. Right? Pi takes it to radians, 180 removes the degrees. So that's theta in radians times the radius 400 millimeters gives us 0.3491. Oh, well, doesn't that look familiar? Right? When I punch that into my calculator, that's where we got here, right? That's the bottom half of this appendage of our length there. It's the same delta that we had gotten going through this long trigway. Right? We can use this theta R estimation, this distance estimation, and get very close to the same thing. Now, it may be off by a couple decimal points after this. You know, maybe it's 0.349147, and the other one had something else. But they're extremely close. So we're saying this is a totally fine shortcut to take, because if I calculate my strain, right, I can use delta over the initial length, 0.3491 over 300. And look at that, I'm going to end up with the exact same strain, 0.00116 millimeters per millimeter. Exact same strain, only took 2 equations to do it instead of a lot of trigonometry. So just keep this nugget in the back of your mind that you can use this small angle shortcut. This S equals theta R is a really good thing to keep in your back pocket, because so much of the deformation we're dealing with is so small. So keep that in mind, especially as we look at shear stress and our shear strain, in our shear strain problem. It's going to be a lot easier to use this small angle theory rather than going through the trig.